Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to talk about how to calculate the wavelength of an electron that undergoes a certain transition in an atom. So let's get started. So in this question we're told what is the wavelength, or we're asked what is the wavelength of the line in the emission spectrum of H plus or helium plus produced by an electronic transition from the n equals 5 to the n equals 2 energy level. So one thing you want to first notice is that we're talking about the He plus ion, not the helium atom. And why is that important? The reason that's important is because if you know that the helium atom has two protons, atomic number of 2, then you know that the helium atom, the neutral helium atom, is going to have 2 electrons. But the He plus ion, because it has a plus charge, that means that it lost one of its electrons, meaning that it has 1 electron left over. Well, why is that important, Mr. Cobalt? Well, I'm glad you asked. Because the reason that's important is because we realize that this is a 1 electron system. And the great thing about 1 electron systems is that we can use the Rydberg equation to calculate the amount of energy that an electron loses or gains when it goes through certain transitions. So what is this equation? So we know that the change in energy of an atom, right, and that includes the electrons in the atom, is going to be equal to negative, let me get that better, minus z squared. So z is the effective nuclear charge, and that's going to be multiplied by 2.18 times 10 to the negative 18 joules, multiplied by 1 over nf squared minus 1 over ni squared. And so what is nf and ni? Well, n is the symbol for the energy level that the electron is in, and F is the final energy level that the electron ends up in, and Ni is the initial or starting energy level that it started in the transition. Okay? So anytime you have a 1 electron system, you can use this to help you calculate the amount of the energy change in an atom when an electron goes through a particular transition. So that's the importance of paying attention to what they give you as far as the atom is concerned. This does not work really well if you have more than 1 electron in the system, right? So in some way, if you have a 1 electron system, then this will work, because this is kind of like what is called a hydrogen-like system or a hydrogen-like atom. Why is it hydrogen-like? It's because hydrogen only has 1 electron in the atom. So any other atom that only has 1 electron but is not hydrogen is like hydrogen in that respect. Okay, so now that we have this, we can plug everything in and solve for the energy change in the atom that has an electron that undergoes this transition. So in this case, this is going to be negative Z. Well, helium has 2 protons, and Z is the symbol for the atomic number, which is the number of protons. So, also known as the nuclear charge. So we're going to put 2 squared times 2.18 times 10 to the negative 18 joules times 1 over NF squared. What's the final energy level? Well, it goes from n equals 5 to n equals 2. So the final energy level is 2. So it's going to be 1 over 2 squared minus, what's the initial energy level? That was beginning in n equals 5. So that's going to be 1 over 5 squared. Okay. So, of course, 1 over 2 squared is 1 over 4 minus 1 over 25. So if we subtract those from each other, and then we multiply these together, let's do this step by step. So this is going to be minus 2 squared times 2.18 times 10 to the negative 18 joules multiplied by 1 over 4 minus 1 over 25. If we subtract these, then we get 1 negative 2 squared, or we can just change this to 4 since that's 2 squared. So minus 4 times 2.18 times 10 to the negative 18 joules multiplied by, and that's going to be 0.21. And then so if we just multiply all of these together, our answer is going to be negative 1.8312. So negative 1.8312 times 10 to the negative 18 joules. So this is the change in the energy of the atom when the electron goes through this transition from 5 to 2. Now, what are they asking us? We want to find the wavelength. So now that we have the change in the atom, we have to relate that to the change in the photon that caused this change in the electron, right? So here we have n equals 5, right? So when the electron goes from n equals 5, that's farther from the nucleus. It's going to go to n equals 2, which is closer to the nucleus. So the electron is moving down. So when the electron goes from a higher energy level to a lower energy level, it's going to lose energy. It loses that energy in the form of a photon. So we need to figure out what the energy of that photon is. So what we need to keep in mind is that the energy change in the atom is going to be related to the energy of the photon. Notice that this energy change is negative. The atom lost energy. Well, where is that energy? It's in the photon. So if I was to write this, I could write it this way. So the change in the energy of the atom, or I should write it this way. So the energy of the photon is going to be equal to negative the energy change of the atom. So whatever the atom energy change here is going to be the minus. So here we have a minus here. So that's going to be equal to minus, and then minus the 1.8312 times 10 to the negative 18 joules. Well, a minus and a minus is a plus when you multiply those. So we get a positive 1.8312 times 10 to the negative 18 joules for the energy of that photon that was released. And this makes sense because photons are not going to have a negative energy. They're only going to have positive energy. Okay, so that's the energy of the photon that was released. Now we just need to figure out what the wavelength is. So we're going to use the energy of the photon is equal to Planck's constant multiplied by nu, which is the frequency. We know that frequency and wavelength are related to the speed of light. So speed of light is equal to wavelength multiplied by the frequency nu. Let me write that better. So nu is the Greek symbol that stands for frequency. So wavelength times frequency gives us the speed of light. So if I want to substitute in wavelength, I want wavelength because they're asking us for wavelength. So then nu here, right? Nu is going to be equal to the speed of light over the wavelength. So now I can substitute this in for nu. So that means that the energy of the photon is equal to Planck's constant times the speed of light over lambda, which is the wavelength. So lambda is the Greek symbol that stands for wavelength. So now I can use this equation, E, the energy of the photon is equal to hc over lambda. Okay, so now all I need to do is solve for lambda. So lambda is going to be equal to hc divided by the energy of the photon. So now all I need to do is plug in Planck's constant, the speed of light, and the energy of the photon that I got here. So here's the energy of the photon. So I'm going to plug that in. I'm going to continue the calculation up here. So lambda is equal to Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds multiplied by speed of light, which is going to be 3.0 times 10 to the 8 meters over seconds divided by the energy of the photon, which I got here. So that's going to be 1.8312 times 10 to the negative 18 joules. And now notice here, look at the units here. They're going to cancel out, right? So joules cancels out, and seconds are going to cancel out, leaving me with meters. So now I can calculate the wavelength of the photon in meters, and when I do that, it's going to be 1.0855 times 10 to the negative 7 meters. Let me double check to make sure I did that right. Negative 7. That is correct. Okay. So then, normally we don't have it in meters. We want it in nanometers because that's usually the unit that the wavelength of light is in, because the wavelengths are so small. Nanometers is a more appropriate unit. So we're going to have to convert meters to nanometers. So use the conversion factor. So we're going to start 1.0855 times 10 to the negative 7 meters over 1. I know 1 nanometer is equal to 1 billionth of a meter because nano means 1 billionth of. So that's going to be 10 to the negative 9. So I'm going to put 10 to the negative 9 meters on the bottom and 1 nanometer on top. So meters cancels out. So now I'm going to divide this by 1 billion. And what do I get? I'm going to get 109 nanometers. So that is the wavelength of light. That's the wavelength associated with the line on the emission spectrum that of the electron that goes from 5 to 2. And again, what do we mean by a emission spectrum? Let me put it this way. Basically, the emission spectrum gives you bands of light at different wavelengths. So increasing wavelength. So each band of light represents a wavelength of a photon that was emitted due to the transition of electron from one energy level to the other. And so basically the problem is asking you, hey, we have this emission spectrum of helium plus ion. This band of light or whatever band of light they're choosing, that one is due to the transition of the electron in the helium plus ion from n equals 5 to n equals 2. And they were asking, what's the wavelength of that light that's associated with that band on the emission spectrum? And that's what we got here. So the 109 nanometers is the wavelength of light of that photon that's emitted due to the electron going from energy level number 5 down to energy level number 2. That's it for this video. I hope you enjoyed the video. If this was helpful or if you enjoyed this in any way, then please by all means like the video, share the video, hit that notification bell or the like button first, somewhere around here. Then do me a favor, subscribe to my channel, hit that notification bell. And when you do, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, let me know. If you have a topic that you would like me to cover, let me know. I would like to do that for you. Thanks for joining me and have a great day.